Hi class, it is me, Professor Williams again, back for our 4.5 section video. This is on harmonic motion. Harmonic motion is very, very important. It actually gets skipped a lot of times in a trigonometry class. However, if you take physics, you have to talk about harmonic motion a lot. If you get all the way up to a differential equations course, you cover harmonic motion in great detail. So it's nice to have a basic understanding of it now so that it's not as hard to deal with later, right? So we're going to talk about basically just using our sine and cosine functions to model behavior of harmonic motion. So harmonic motion basically is anything that kind of goes back and forth. You can think about a swing. You can think about a weight on a pendulum. Typically what we start off with though is a weight on a spring, right? So we're going to talk about simple harmonic motion, and then we will talk about damped oscillatory motion as well. So our first instance is a mass on a spring. Okay, so our spring is being suspended from a ceiling or being held, or something is holding it, and when the weight gets put on the spring, it pulls it down due to the force of gravity, right? So we call this the equilibrium position or the rest position. Okay, it's how far the spring naturally stretches when whatever size weight we put on it. So obviously if we put on a heavier weight, it's going to stretch the string more. We would call that our equilibrium position for that weight. The weight was lighter, it would stretch it less. And where it rests at, that's our equilibrium position for, again, that weight that we put on. Okay. So if the weight is pulled down A units, okay, and then we release it, right, for instance, what's going to happen is that the spring force tension of the spring is going to pull the weight up. And that's going to start our oscillation or our harmonic motion, right? So the elasticity of the spring, which is a constant value, will cause A to then go to a positive position. So here we're calling this the downward force because we're pulling it down. So our A is negative, and the elasticity of the spring, right, the spring constant, will force the spring back up above the equilibrium point to a positive value. Okay, generally, however much you pull it down is how much it will rise, right? So if you pull it down by a value of A, you will, it will react and bring it to a height of A above the equilibrium position, okay? Which is what we're calling C. So we start with A, we pull it down, the spring will counteract this force of gravity because of the tension in the spring, and it will pull it up to A, right? So as you can imagine, we're basically then going to start an oscillation that goes below the zero value, the equilibrium position, and above over and over and over again by a value of A, right? So A then is then what we call our amplitude, right? We've seen this before. So the amplitude will be A, and it will start to oscillate in a manner that coincides with what we could call a sine wave or a cosine wave, right? It'll start an oscillation. So, as part C, it'll oscillate about the equilibrium position of 0, okay? So the position of a point oscillating about an equilibrium position at time t is modeled by either S of t, which is an amplitude times cosine times omega t, where S of t is an amplitude amount times sine of omega t, okay? Where A and omega are constant values, okay? Here, omega has to be a positive value that is larger than 0, okay? And the amplitude of the motion is the absolute value of A. And the period is 2 pi divided by omega, okay? And our frequency is the reciprocal of that, omega divided by 2 pi, right? And that's given in oscillations per time unit. So let's start off by building a model, right? So let's model the motion of a spring. So suppose that an object is attached to a coiled spring. It is pulled down a distance of 5 inches from its equilibrium position and then released. So identical to what we had here, right? We're going to pull it down 5 inches and release it. Okay. The time for one complete oscillation. So if I pull it down, the time it takes for it to come back down is 4 seconds. Okay, so we want to give an equation that models the position of the object at time t. So when the object is released, we call that time 0, or t equals 0, and the object has a distance of -5 inches from the equilibrium. Okay, so it's 5 inches down from the equilibrium. So s of 0 is going to be -5. Okay. So if I'm looking at that as a cosine omega of 0, right? So remember, cosine of 0 is always 1. So that gives me an a value or an amplitude of -5 here. Okay. Absolute value wise, amplitude is 5. But the value of a here is -5 since we're starting in the downward position. Right. So we choose the cosine function because we know that cosine of 0 is going to be 1. Okay. So we use the fact that the period is 4 to solve for my value of omega, right? Because now I have basically everything solved for except for omega. So I will use that I know what the period is with my formula for the period, right? So 2 pi over omega will be 4. The only unknown value will be omega, right? So you multiply it by omega, divide by 4, we will have 1/2 pi. So multiply by omega, divide by 4. We get 2 pi over 4, or 2/4 pi, or 1/2 pi, or pi over 2, however you want to call it, right? So that's our motion is going to be modeled by the function s of t is -5 cosine pi over 2t. Okay, so we just had to find the individual pieces to finish out the model for our harmonic motion. Okay, so part B, we want to determine the position at time equals 1.5. Well, luckily, us smart, wonderful trig people here just found an equation to use, right? So all we have to do is plug in -1.5 here. It would probably be much easier to plug in that as a fraction. So let's plug in not negative, it's always positive. Let's plug in 3/2. Okay, so we can have 3/2, that'll give us 3 pi over 4. That'll be a little bit easier for us to use in terms of radians. Okay, plug this in and get 3.54 inches. So I will be, notice that my value is positive. That means that I will be above the equilibrium position. Okay, so if I pulled it down 5 inches, after a second and a half, I will be at that value that we just found above the equilibrium position because my value is positive. Okay, what do we have? 3.54 inches. Okay, and so since this value is positive, at a second and a half, the object is above the equilibrium position. Okay, so next we want to find the frequency. That's super easy, right? Remember, the frequency is just the reciprocal of the period that we have. Okay, so the frequency was 1/4 oscillation per period. Okay, so I'm sorry, because we had a period of 4, right? The period is 4, so the frequency is 1/4. So that was an easy one, right? So example 2, let's analyze this harmonic motion. So let's suppose that an object oscillates according to the model s of t equals 8 sine 3t. So we know that my amplitude is 8, and we can figure out what the period and the frequency is here by either dividing by 2 pi or by dividing 2 pi by 3, right? So t is in seconds in this case, and s of t is in feet. Okay, So we want to analyze the motion. So we just did a really quick analysis, right? So I know that I am starting this off where it has an amplitude of 8 feet, right? Because everything's in feet here. So the motion of is harmonic because the model follows that formula that we have for harmonic motion. It just happens to be sine instead of cosine this time. My A value is 8, so it oscillates 8 feet in either direction about the equilibrium point. Okay, the period is going to be 2 pi divided by 3. Okay, so that comes to around 2.1 seconds for one period, and this is in seconds, right? For complete oscillation. For my frequency, it is the reciprocal of that, or 0.48 oscillations per second. Okay. So now let's talk about damped oscillatory motion. So a damping of oscillatory motion means that we have a retarding force. Okay, we have something slowing down our mass on a spring, right? Now this could be just standard friction, right? Which is not very dampening, actually, honestly. We can have our spring and weight dipping into a liquid. Okay, it could be dipping into water, it could be dipping into oil, things that are slowing its motion down. These things are all very important when we talk about things like retrofitting a building for earthquake motion, right? Because what happens during an earthquake is a building will shake, it'll oscillate to the point that it breaks and it topples and falls over. So we have dampening springs to dampen that oscillation motion of a building in an earthquake. Okay. Again, here it even states that most oscillatory motions are damped by friction and air resistance, which is a form of friction, and causes the amplitude of the motion to decrease gradually until your weight eventually comes to rest, right? So this motion can be modeled by e to the negative t times sine of t. So if you notice here, this is e to a negative exponent as a function, right? It is a decreasing exponential function. So if you attach that to your sine, you will have a single oscillation and then it'll start to come to rest, right? So that is one way of modeling a dampening motion. There's also other models which we may or may not talk about here. But notice that this is my standard sine function. This is the e to the negative t. This is just a negative e to the t in case we have, a negative form of a function. But when we put these things together, the e to the negative t sine t, the motion looks like this solid magenta line that we have here. Okay. So a typical example of damped oscillatory motion is provided by this following function. Let's say s of x equals e to the negative x times cosine 2 pi x. Okay, that would be an example. So the number e, right, this base here, it is a irrational number, much like pi. It goes on forever. It does not stop. However, we can round it to a certain decimal place for whatever desired accuracy that we need. So it says approximately 2.718. I think the exact first four terms is 2.7176 or something like that. So this is the base of the natural log function, right? So here we're going to use x rather than t just to match what happens in the calculator, right? So let's say we want to provide a calculator graph of a y function that is e to negative x times cosine 2 pi x, along with two other functions, one of them being e to the negative x and y being negative e to the negative x. So it'll look very, very similar to what we had over here, right? Where we're going to have an e to the negative x and negative e to the x. So we'll have these two exponential functions, and then we'll have our damped functions. The only difference is that it'll be e to the negative x sine to the 2 pi x, right? So this is going to extend our period, or I'm sorry, it's going to shorten our period just a little bit, right? Or quite a bit, actually. Okay. So we're going to graph those three, and we just want to put in the viewing window from 0 to 3. So we're going to graph those three functions. Maybe you want to go ahead and pause and do that yourself here. Maybe I'll do that with you. Let me see if I have a calculator on my computer that I can use. 1 second. Okay, and we're back. So I don't have a TI calculator online for me to use, but I prefer to use Desmos when possible. So let's go ahead and do one of these functions. Okay, and let's do the other one. Hopefully you can guess which one is which. Okay, so I have my e to the negative x. I have my negative e to the negative x. And then we can have our final function, which is the e to the negative x times sine 2 pi x. Okay, so as you can see, I am stuck in between the two other functions. Okay, right? So obviously it goes without bounds, right? Because this goes to negative infinity, this goes to infinity. But we're really only interested in the things that are happening from 0 forward. Oops. Okay. For both of these, for all of these functions, really. So that's what I'm interested in. You can blow these up and make them larger. Okay, so this is what my oscillation looks like, and it asks us really to only go to 3, but let's play around a little bit and notice what happens when we get really close. Okay, so again, these values will always approach 0, right? They're sandwiching my function, but my function continues to oscillate. Very, very small, right? The period is still the same, but it oscillates within the bounds of the upper and the lower function that's given by e to the negative x, this red line, and f to the negative x, which is the lower line. Okay, so that's what your graph should look like. Of course, it asks you to cut off at 3, right? So we kind of just looked a little bit deeper than that. Deborah, and we're back, right? So obviously this PowerPoint is probably going to have a graph of this as well. Okay, and again, look, it's very similar. It's obviously not in Desmos, but you know, they use their own graphing software to graph this for you, and it matches up with what we had, right? So B. So again, let's look at this, right? So this is a damping, right? I'm oscillating, but I'm slowly going towards my equilibrium position. Okay, so B. Describe the relationships among the 3 graphs drawn in part A. So the graph of y3, which was the first one, was my upper bound. Or I'm sorry, this was my oscillation. y1 is my upper bound. It never goes above this. And y2 is my lower bound. It never goes below that value. Okay, so the graph of y3 is bounded above by the graph of y1, and it's bounded below by the graph of y2. Right? So we refer to these as envelopes for the graph of y3. Okay. So for what values of x does the graph of y3 touch the graph of y1? So it happens at the tops of all of the oscillations. Okay. So if you notice, it's every other, it's at the end of a period. So that's when 2 pi of x equals 0. So that's going to be 2 pi, 4 pi, 6 pi, and so forth. Okay, or when cosine of 2 pi x equals 1. So the values of e to the negative x cosine 2 pi x is the same as the value of e to the negative x when 2 pi x is 0, 2 pi, 4 pi, and 6 pi. Okay, so that's when they are touching. Okay, so when x is 0, 1, 2, and 3. So part D says, for what values of x does the graph of y3 intersect the x-axis? Okay. So when is it crossing? And that's going to be when our function e to negative x cosine 2 pi x is equal to 0. So apologies, I guess I did the sine function on my graph because I did it in haste, but obviously it looks the same, right? So I want to know when, for D, is when this is equal to 0. Okay, so that's going to be when 2 pi x is pi over 2, 3 pi over 2, 5 pi over 2, 7 pi, and so forth. And so again, you can do this, you can check this out by using your trace function on your calculator, or you can set up a matrix, or I'm sorry, your equation equal to 0, and then solve for cosine 2 pi x equaling 0. Okay, so the graph of y3 intersects the x-axis when x is going to be 1/4, 3/4, 5/4, 7/4, 9/4, and 11/4. Okay. Thank you guys.